I will talk about work with Brown methods in Leiden. We have been working on this for a year now. So we defined a Laplace type operator on Ahlfors regular spaces. It's not too difficult to define it, but what's challenging is to prove properties about this operator, because the setting is quite general. So it has the word logarithmic because the eigenvalues of this operator grow slowly, and it does not come from any functional calculus on any well-known Laplacian. Right. I should start by the fractional Laplacian on Rn, which is a really important operator. And Parelli, for example, this year he got the Abel Prize, and his most cited paper was about the study of this operator here, the Laplacian, because it has so diverse applications in many areas: biology, physics, finance. So how do you define this operator? You have the actual Laplacian on the end, and then you do functional calculus, right? And you have some nice descriptions of it. Via Fourier transform, you get that this fractional operator, this fractional power, has this symbol psi to the alpha, right? But it also has a really nice integral representation. This one here, and constants that depends on the dimension and this fractional parameter alpha. Now this operator is non-local in the sense that delta at f in general will not have support related to the support of f. For example, if f of x is 0, then this most typically will not be 0. Because you remove this term, but you keep this one. It also has a singularity on the diagonal, so it explodes, but it's integrable outside of the diagonal because we have this plus alpha parameter. And it has at least 10 equivalent descriptions, literally, because, well, we are in Rn, and also people were very interested to find many descriptions applied to many situations. For example, it generates a really nice Markov process here called alpha stable Levy process. It's also possible to define it on openly connected subsets of Rn, which are bound domains, and then you want to study the Markov process on this bounded domain, exiting times and stuff like that. And the typical way to do it is you consider functions on a Rn, and then you restrict them on the domain. And then you restrict this operator, basically. And because, in this case, we need to impose boundary conditions, there is really non-consensus of what the fractional Laplacian should be on bounded domains. And, right. Quite recently, the logarithmic Laplacian was defined on Rn, and it doesn't come from taking functional calculus with the logarithm on the actual Laplacian. Okay? Although it turns out it's related because we are still in Rn. It has a similar description, but we don't have the plus alpha here, so this kernel is not integrable outside of the diagonal. And so you need to localize, I have forgot here, it should be the characteristic function of the unit ball at y, right? So you localize, so it makes sense of the integral. And the symbol is 2 log psi. And for this reason, it's related to the logarithm, to the functional calculus with the logarithm on here, but it's not really the same. Again, it's a non-local operator, and it's related to bit weird process, the variance gamma process. But it's very also important to finance from what I've been told. You can do the same trick. You restrict it on bounded domains with boundary conditions. And here's the difference with the fractional Laplacian. If the domain has very large volume, this operator will not be positive definite. Whereas this is always. And on the bounded domains. And in both situations, we have bounded domains, and this means we cannot really apply it to compact subsets of Rn, because you cannot restrict the function on a compact subset and make it zero everywhere else and expect the function to be inside the domain of the operator. All right, and this is what we try to solve. So we go to regular spaces, meaning spaces with a nice metric spaces, with a nice measure. So we have a Borel measure. This talk we restrict to finite. Borel measure, and we assume this regularity condition that you have some control on the volume of the ball. If you have such, then delta will be the Hausdorff and box counting dimension, and like most of fractal dimensions that you can think will be equal to delta. Although it's a strong condition for a measure, you have many examples that metric spaces that have such a measure. Compact Riemannian manifolds connected. Several fractals in Rn have such measure. The Hausdorff measure will be out of regular, and many examples from hyperbolic dynamical systems, Smale spaces and Gromov boundaries of hyperbolic groups have this. So here you have the Bowen measure, that maximizes the topological entropy, and here you have the Patterson-Sullivan measure. So they are Ahlfors regular. And our goal is to define a Laplace type operator on Ahlfors regular spaces, and so being able to do analysis on these spaces. All right, how can we do this? Well, that's the sensible thing to do. We try to define intrinsically an operator for the space X. So we shall restrict to real vector spaces, and of course you can complexify everything. But we restrict to real because in the literature people study real Hilbert spaces. So we also want to appeal to this audience. Right, so you consider all the L2 functions that have this integral to converge. This really gives a semi-norm on this space, and then you can equip this with an inner product. And in fact, this comes from a quadratic form. Okay, so what we want to do here, it's like something quite easy. It's a Riesz representation at this level. Because this 4 is symmetric, it's positive, and turns out it's also closed. Okay? This means this logarithmic Sobolev space is actually a Hilbert space, so the definition is correct. All right. And then from Riesz representation, we can find a densely defined positive self-adjoint operator on L2 with domain inside this logarithmic Sobolev space. And the Sobolev space is really equal to the domain of the square root of this operator. And we call this the logarithmic Dirichlet Laplacian. So far, nothing has been done. I mean, non-trivial theorems have been used, but nothing has been done. So some first observations about this operator are the following. the kernel of it is constant. And the limits are all the L2 functions that integrate to 0. Right? And further, the domain of this operator is literally choose. It contains all Holder functions of any exponent. In fact, every Dean continuous function, if you know what Dean continuous is, the modulus of continuity. And in fact, contains like some generalization of Holder functions, which are called the Hausdorff functions, like weakly Holder, in the sense that they have weak gradients. They don't need to be continuous. And on these spaces, subspaces, yeah, all these are in the domain of the Laplacian, and on these the Laplacian has this integral representation here. So I shall go back, and you can see that, well, the kernel here is the dimension of the space, the Hausdorff dimension. So we get the same kernel, basically with the logarithmic Laplacian here. But in our situation, the operator, this one here, is always positive, no matter how large the volume of this is. Whereas here, if you restrict this on a bounded domain, and the volume is large, then the first eigenvalue is going to be negative. So they're related, but not really, not in every case. All right. So we have this nice integral representation that allows us to do computations. But one needs, that was, up to this point, there's nothing too difficult. But what is difficult is to prove nice properties about this operator. And the core, for example, or domain. Let's see an example first. The operator, the logarithmic Laplacian, on the space of infinite words of 0 and 1. Okay, this is a counterset. You equip this with a Bernoulli measure and with this not sensible metric. You just so the distance of two sequences really depends on how for how long the sequences from the start agree. Okay, and the first time that you see a different letter, you stop. Now the Bernoulli measure is Ahlfors regular, delta is equal to 1. And now you can diagonalize this, and these are the spectral projections. And how do you do this? Well, you have cylinder sets in this space, in this counterset, and you keep refining them. So at the first level, the cylinder sets will depend on the first word of the infinite sequences. At the second level, you have two words, and you keep going like it. So you build a tree, a dyadic tree, and you have characteristic functions on them, and then you take the projections on each level, and then you take the difference of consecutive projections, and this will give you wavelets, a hard basis. And so if you take a wavelet of level n in this construction, its eigenvalue will be therefore, this operator is essentially self-adjoint on Lipschitz functions. This is what you get from this diagonalization. And it has compact resolvent. In particular, this heat semigroup is compact, consists of compact operators. And for every t greater than 2 times the logarithm of 2, the operators are trace plus, because, I mean, this grows n over 2, and the eigenspaces have dimension 2 to the n minus 1, 2 to the n. And this is, from this you get this number, and this is sharp, meaning that for t equal to this or smaller than this is no longer a trace class. And for t smaller than this over 2, it's not even Hilbert speed. Okay, so you don't have a nice kernel. And this has implications to the hit kernel. So it's not going to be nice. Now, what's interesting in this situation is that this number, you can do this not just for the 2-shift, but for topological Markov chains. Here, you will get the logarithm of the Perron-Frobenius eigenvalue. So you get the entropy. This bound, the lower bound, the sharp lower bound, does not depend on the metric. I don't understand this yet. And so if you change the expanding factor here, it will not appear. If you change the expanding factor, the dimension will change. This will not appear. Not there. Another example, the unit interval. I give you the unit interval, you might think it's trivial, but it's not, because it has boundary. And usually, if you have boundary conditions, you will not get essential self-adjointments, but this is an intrinsic operator. Okay. The unit interval, the Lebesgue measure, and of course the Euclidean metric. The dimension is 1. So how do you diagonalize the Dirichlet Laplacian, the logarithmic Dirichlet Laplacian? Well, you just evaluate it on the monomials x to the n, and then you use this identity, right? And so with this, you can just kill the kernel, and you just integrate this part, basically. So you can get a closed formula for the image of this under the and this is an ophthalmological test for back roads. So do you see the eigenvalues here? So this is 1, 3 over 2, 11 over 6, 25 over 12, 137 over 60. Anyone knows what these eigenvalues, what this sequence is? Can guess? I mean, well, they are the harmonic numbers, exactly. It's the sequence of harmonic numbers. And I divided by 1 over 2, this is not important. It's how you define the Laplacian. Okay? So you have an operator where the harmonic numbers, all of them, are the eigenvalues. They are simple eigenvalues. And the eigenfunctions are the Legendre polynomials. And the cutoff in this case is 1 over 2. And as I said, we don't really understand what the cutoff means. It should be some sort of volume in the space, but don't know what kind of volume yet, because before we were getting the topological entropy, and here you don't use any dynamics of the space. Right, but I would nice that so you get I'm happy. So can we say something like that for the general situation of the Laplacian on Ahlfors regular spaces? Well, yes. The logarithmic Dirichlet Laplacian turns out to be essentially self-adjoint on Lipschitz functions. And it's not very easy to show. But what does it mean? It means that, well, Lipschitz functions are a core domain for this. Equivalently, if I go back, if we start with such an operator, densely defined on Lipschitz functions, it's symmetric, right? So we'll have self-adjoint extensions. This one, the Dirichlet, will be the unique self-adjoint extension. This is what it means. And moreover, the essential self-adjointness on continuous functions from general theory of Fukushima really tells us that we get the Markov process here. I don't know if it's going to be some kind of variance gamma process, like we get in the case of Rn. It's open for study, I guess. And this operator has compact resolvents, and in fact, Lie-1 summable resolvents, meaning that again you have similar behavior here. You get a cutoff for so all these operators will be compact. Oh, here I should have put L delta. I'm sorry, that's type. Yeah. So all these operators will be compact, and they will be trace class for all t greater than some t0. But in the general situation, we don't know if this t0 is sharp. For the examples I've shown you, we recover the numbers, the cutoff numbers, but in general, we don't know. Some sort of way law is required to get the sharp. And this operator also gives a spectral triple, a Lie-1 summable spectral triple. So if you take a Lipschitz function and you commute it with this logarithmic Laplacian, it will be a Calderon-Zygmuth operator. It will be bounded. And this self-adjointness on Lipschitz functions really tells us that Lipschitz functions map the domain of the Laplacian to the domain. Okay. All right. Now, our methods also allows us to compare the logarithmic Laplacian with the fractional Dirichlet Laplacian on an Ahlfors regular space. You can also define fractional Dirichlet Laplacian, and so instead of having the kernel only to the power minus delta, you also put the plus alpha. You make things integrable. I mean, but you're in a finite space, so you don't really need to worry about it for this talk. Now, this Laplacian has been studied a lot, but in terms of its square root, and this is something very, very different from studying the Laplacian itself. Because, for instance, if you have a core domain for this, typically, I mean, it should be a really nice core domain, but typically it will not be a core domain for delta. And people were using this Laplacian, I mean, the square root of this Laplacian to study Markov processes on metric spaces. And there exists a Holder continuous heat kernel, but in this generality, the regularity of the heat kernel, the Holder exponent, is not good enough to allow us to say that this Laplacian is essentially self-adjoint on some Holder functions. Okay. So, with the methods we created to study the logarithmic Laplacian, we were able also to show the following. Well, the first 2 points are, I mean, you don't need the methods that we contracted. I mean, again, the kernel is the constants, and this has a lot smaller domain than the logarithmic Laplacian. But we were able to show that delta alpha is essentially self-adjoint on every Holder continuous function with exponents strictly less than 1. This has to do with the fact that we have this plus alpha. And somehow it's not clear if we can reduce this to all Lipschitz functions. But still, it's for everything we want to do, having almost Lipschitz functions works. Now this has finitely summable resolvent. And in fact, we get again a spectral triple, this time finitely summable, for every p greater than delta, the Hausdorff dimension over alpha, the fractional parameter. And in fact, this is sharp. This is a spectral dimension of the spectral triple. will not be anti-summable or be equal to this or less than that. So you have a while law for this. Now, to finish, the main motivation for studying, for investigating this operator is because it allows to create spectral triples on purely infinite Caesar algebras coming from non-isometric group actions, like Gromov, cross products of Gromov boundary, Gromov boundaries from their groups. And what's interesting is that if you try to inflate this fractional Laplacian, so suppose that you have the Gromov boundary, and so you consider now this fractional Laplacian on the Gromov boundary, and if you try to inflate it to the cross product, it will not be a spectral triple. Commutators will not be bounded. But they will be for the logarithmic Dirichlet Laplacian. Because the eigenvalues grow slowly, but it's not that you see it from studying the eigenvalues. You see it really on the computation of the commutators. If you have this alpha, it explodes. And I should say again that on these metric spaces, we don't have a natural Laplacian. We don't have a local operator that you can just take the logarithm, the functional calculus, the logarithm, and update it. And in fact, try to find a nice local operator with nice properties on a metric space is an open problem in geometric measurement. And these operators are non-local. And being non-local is really, it really means that it's very difficult to diagonalize. Because if you had an eigenfunction, then you would have lambda delta of f is equal to f. This means that the support of f and its image under lambda delta should be the same. Right? That's non-local, it's the opposite case. And before, in the examples that I showed you how to diagonalize them, these wavelets are very particular. It means that they allow you to localize this non-local operator. So it would be interesting to study spectral theory on this Dirichlet Laplacian and the Markov process it generates. Goffin, Rennie, and Usatsev, they have a theory on how to construct KMS states from B1 summable spectral triples. So that would be interesting. To use these B1 summable spectral triples and over cross products to study KMS states. And I don't know if there is any relation to quantum metric spaces. Maybe the non-locality creates difficulties there, but if you try to localize stuff,